We have explained some content in this slide, problematic data. We mainly focus on how to do downsampling, how to do upsampling to deal with unbalanced data. Let's go to here. Some example of overfit or underfit. When we talk about overfit or underfit of a model, we usually means if your model is overfitted, which means your model is too complex. Your model has too many weights, so that your capacity of your model is very large. So in that case, your model can easily remember the relationship between your data, input data, and output target Y. It just simply remember the answer because it has many weights, many neurons, and they can use different neurons to remember specific answer of a specific input. So on the contrary, underfit means your neural network has only very few neurons or layers, so the capacity of your neural network is very small, so that your model cannot correctly present the relationship between your input and output. The data we use as the demonstration right here is not neural network. Okay, it's just a very simple nonlinear regression. The true function, which means the actual function, and we have several different training data set and testing data set. Usually when we do machine learning or neural network, we have an assumption, which is your distribution of your training data set and your testing data set should be the same, at least should be similar. Okay, and I think that is a very nice example. You can see that the true function is the actual distribution. So the sampled training data, which is quite close to the true function, and the sample testing data is quite close to the true function. So that we can learn this true function by using the black dot, which is the training data set. So we believe no matter what kind of regression model we use or the neural network model we use, they can try to represent the blue line by using the black dots. So when we do testing, which is the red dots, our model can do such kind of prediction. For example, that is X and that is Y, that is our target. So every time it's right here, we can successfully predict its target. Every time the new data point, testing data point right here, I can predict its target. Okay, because I have those black data points. Sometimes when you collect those data points, one problem is your training data point, which is the black dot, does not quite fit to the true function. That means you have bias. If your neural network is not perform quite good, maybe you only collect the data right here. So you think, okay, this data set might look quite easy because it looks like linear. So you may create a wrong regression line such like this. You cannot correctly represent the data at the right hand side because it's simply just a very simple line to represent the data at the left hand side. But this is the problem of data collection. You do not collect the entire distribution, which is the blue line. When you do such kind of training and testing, make sure your tested data point has the same range as your training data point. I think the most of model may fail is due to the following reason. Okay, you have a very nice sample, which is all those black data points. Okay, you model all those data points. However, when you do testing, your testing looks like this. That means when you collect your testing data, your data does not fit to your true function. How it happens? For example, if we collect the training data, okay, for example, the black data point, you collect the children's weight and height from an elementary school. So you create a model, you can perfectly describe the training data. However, when you do such kind of testing, you use students in university. However, you cannot guarantee the distribution of data in an elementary school and the data in university is the same unless you can prove it first. For example, if you would like to study some data in Taiwan, but you use the model created from some other region, for example, from the United States, maybe the distribution of the data in Taiwan and in the United States is the same, but most of the time they're not. So some projects they fail. They fails because the model is correct. They can perfectly fit the training data, but the testing data is some irrelevant data. Try to so that is one of the reason. But the other reason is that I think we have talked about before. You use a wrong model. For example, the true function is the blue line, and your observation is the black dot. However, it looks like a nonlinear relationship between your x and y, right? But use a linear model. Okay, if you use your test data right here, your prediction will be very, very worse. If you use a more complex model like neural network, you have many different layers, you have many different neurons, you choose some very advanced activation function to simulate their non-linear relationship. Most likely, your model will try to fit such kind of nonlinear data. Okay, let's take a look at this overfitting problems. The true function is the blue line, and your observation, your training data is the black dot. But you can see that your model is too complex. So you can see that your model try to remember the result of your black dot. Because the capacity of your model, as we can see that right here. Of course, this example is a polynomial example. This is quite complex. You have too many weights. For example, we have 26 weights right here. If we have too many weights, we can remember the data. I would like to draw a figure right here. For example, if we have only very few input, for example, x1, x2, and we have an output y right here. For example, if we have n data, so let's make it very small. So if we have only 5 data, like this. If we have only 5 data, if we have many hidden neurons right here, a very simple neural network structure, but we have too many neurons right here. So when the very first data comes here, we can put it for example right here, S1, S2, and Y right here, right? So if the data right here, that is 2 and 5, and the result is, for example, 8. That is the very first data you will. So when 2 and 5 comes here, and we say this is a neural network, so we connect the relationship right here. If your neural network is very, very complex, which means you have many weights, your capacity is very, very high. You can use a neuron right here, here's H1. This specific neuron H1, it's only focused on the very first data. So the weight right here is 1, the weight right here is 1. We can say that this neuron only specific used for the very first data set. So it can output, for example, it can output 8. Of course, you can tweak this weight, which is okay, this weight, which is okay. So that means this neuron H1, it does not activate for all the other data set. It is possible if you have a very large neural network. I can even draw a very strange neural network. Each neuron has for example, has a convolution layer. The second convolution is 3 and 7, and so on and so forth. The last convolution is 7 and 2. We can create a very specific convolution layer, which means, of course, every data, has to every convolution. But only the first convolution kernel right here is only active to your first data set, first data point. So it will be activated right here. So H1 will output 8, for example. The rest of course, H1 will be connected to some other convolution layer. But this value, 3 and 7, the weight it does not active to 5. It only active to your second data point. So every time when you input your Second data point, 3 and 7. The first neuron, the first convolution kernel will not activate such kind of data. Only this one will activate its data. So after that, a specific neuron H2 will output, for example, 1, 1 right here. So let's, of course, it is a very strange example. I use the word remember or memorize. They can memorize the input and output if you have a very large and very specific neural network. It can do so. So such kind of neural network only memorize the data. Okay? If you input a new testing data, for example, right here, if you have a new testing data, it is 1 and 2. And you will figure out that all those convolution structure right here would not activate such kind of input data, so that it may not output the correct Y. Maybe the answer is 3. So that kind of neural net is extremely overfitted because you have too many weights, and the capacity of this neural net is very, very large enough to that the neuron to remember certain input data and its corresponding output Y. So in this case, we don't want to do so. So we introduce several different techniques. For example, we can use dropout so that some of the neuron will not receive specific data. Okay, those data are randomly dropped when we do such kind of training. So each neuron right here at the right hand side, they will try to receive information from different sources, not a specific sources. So that's the reason why dropout works. Okay, and then next one, which means every time when you create your neural network, don't make it too complex. Complex neural network only fit to very, very large data set. If you have only few hundred or few thousands data points, you don't have to create a very, very complex neural network, because that kind of neural network would tend to memorize the relationship between your X and Y. Okay, we have another approach to deal with such kind of overfit or underfitting. It's called validation data set. My recommendation is after you collect your data, okay, you partition your data into 3 different data sets. One for training, the other for testing, and the other for validation. And you have to make sure all those 3 data sets has the same partial differentiation. You use the data set in your training. And of course, as we mentioned in the previous hour, you can partition your data into some mini batch, okay? And you train your data using this mini batch, okay? That is training data, okay? At the end of your training, you use your data set, tested data set, to calculate how good your model currently is. Of course, you don't train your tested data in when you do training. Okay, so test data only used once when at the end of your training, and that is your result. That is your test result. How about the third data set, which is validation? Every time when you train your data, your model, you do the partial differentiation, you update your MSE or cross entropy. Every time when you train your data, you use your validation dataset to do validation. So, for example, if you train your data 100 times, you have 100 times of partial differentiation to improve your data. Okay, so every time you finish your partial differentiation, you test your current model by using your validation dataset. Of course, it gives you the accuracy of your current model. It gives you your loss value. So you have to observe something like this. When you do the validation, you can observe the current loss. Okay, if the current loss value, okay, like this, right? Loss of validation, and we have different at 1 to 100, and usually the loss function may look like this. Initially it decreased and will stay somewhere, which means your model is quite stable when you try to do further training. Okay, those data points would not further decrease your loss value. So you can use the validation function, validation dataset to test if your loss value will stay somewhere stable value. Okay, if you keep training your data many times, which means you have several different runs, those n data, you use them multiple times, 100 times, 1000 times. Okay, in that cases, okay, your training accuracy will be very high. That is because your model now will try to memorize the data right here and its corresponding target value. That means your model will gradually become overfitted. Okay, so in this case, since your validation data has never been trained, you can see that your validation data's loss will become higher and higher because your model, currently your neural network model, will currently has been trained too many times by using your training data. So your neural network will try to memorize the answer between your x and y. 你的模型失去了一般性，它越来越专一化了，因为你 training data 太多次了。So we can use validation dataset to verify if your model become more and more specific to the training dataset. Okay, so maybe you should stop your training right here. So we call it early stop. Okay, you can find some settings in Keras or TensorFlow. Okay, they teach you how to stop your model early. So after you do such kind of early stop, okay, you don't do training again. Then you test your data, and that is your result. Okay, of course you can. There's a parameter right here for your validation. Okay, if your loss of validation is quite stable and it suddenly regress, okay, you can define what it means suddenly. There's a threshold right there. If it suddenly decreases, then you should stop your model. Your model becomes too overfitted. It says degree, that means because the example is polynomial, but we can use exactly the same thing right here. Every time when you do the training, if you don't want your model to be overfitted, okay, you can set different number of layers and neurons, and you can set different runs of your epoch to do training. So the result will be like the same. Your training error will be less and less and less. That is because your model is overfitted. So sometimes you need another dataset to help you. Okay, you should not do training anymore. You should stop right here. That is good enough. Right here is the regularization, which we have talked before. Reg and the lasso regression. When you design your loss function, okay, remember, okay, add something like here. The theta is all the weight. We have to minimize this weight so that some of the weight will become 0. That means some of the neuron will not activated. Maybe you have too many neurons, too many weights to describe a problem, right? But after you apply this, some of the neuron dies. The capacity of your model, which is the number of weights you want to use, decrease. That means it helps your model to only keep some of the neurons, not all of them, so that your model may prevent overfitting. Okay, so remember to use these things. Of course, there's a weight over here, so you can try to balance between how many neurons you would like to make them die, or you would like to minimize your loss. Okay.